Hi everyone, this is the second in a series of two videos where I'm covering the theoretical trig component for the International Baccalaureate course Maths Standard. In this video I'm going to go through exact values, boundary values, gradient, trigonometric identities from the unit circle, proofs, and finish off with trigonometric equations. Let's begin with exact values. There are 9 exact values that you need to memorize, and they are for the angles 30 degrees, 45 degrees, and 60 degrees. Now the first two, the 30 degrees and the 60 degrees, comes from this triangle here. It's an equilateral triangle with sides of length 2. And so this is 2 here. When we drop this perpendicular here, it's going to bisect this side, and that means that this distance here is going to be 1. Now, of course, an equilateral triangle has angles of 60, and if I take into account this 90, then that angle up there is going to be 30 degrees. So that's where I'm getting my 30 and my 60 from. The other thing I need to do is work out the distance here, and I'm just going to use Pythagoras' theorem to do that. So I'm going to do 4 take away 1 is 3, and then do the square root. And so that height there is going to be root 3. Okay, from that we know that sine 30, which is also equal to sine pi on 6, that's in radians, is going to be equal to 1 over 2. So sine 30 is a half. Cos 30 is equal to adjacent over hypotenuse, so root 3 over 2. And tan 30 is equal to opposite over adjacent, 1 over root 3. So there's our exact values for 30 degrees. Now let's do them for 60 degrees. It's the same diagram. So sine of 60 is root 3 on 2. Cos of 60 is a half. Probably notice the complementary ratios there. So this is exactly the same as cos 30. And this one's the same as sine 30. And then tan 60 is root 3 on 1, or just root 3. This is the triangle that we use for 45 degrees. It's an isosceles triangle with side length of 1. So that means that this is going to be 45 degrees here and 45 degrees here. Again, we need to do Pythagoras' theorem and work this distance out. It's going to be 1 squared plus 1 squared is 2. Then do the square root, gives us root 2 along here. Okay, sine 45, which is sine pi on 4, is 1 over root 2. So is cos 45, 1 over root 2, and tan 45 is 1. We can find the exact values for any multiples of 30, 45, or 60 by using the all stations to central diagram. Do you remember that? So let's say we want to find the exact value of sine 330. We've got to think about which quadrant that's in. It's going to be in that 4th quadrant. So let's just draw that up. I've got all stations to central. And it's going to be down in here. And that's the 360 minus theta quadrant. So I want to rewrite that as sine 360 minus 30. The next thing we've got to think about is whether sine is positive or negative in that quadrant. And down here, this C is telling us that only cosine is positive, so sine is negative. So sine 330 is going to be exactly equivalent to negative sine 30. And we just worked out that sine 30 is a half. So sine 330 will equal negative a half. Here's another one. So we've got this time in radians cos 3 pi on 4. Okay, so let's think about where that is. Now, it's a little bit more tricky to figure this out in radians, but this is pi over here, and this is 2 pi up here, and that's less than 1 3/4, so it's going to be up in here. And I'm going to rewrite it as pi minus pi on 4. So that'll give me cos pi take away pi on 4. Alright, in this quadrant in here, cos is going to be negative. So it's going to be equal to negative cos of pi on 4. and cos of pi on 4 is 1 on root 2. Now you might need to practice these for a bit, they are tricky. Last one, tan of 4 pi on 3. Now you can see how I'm greater than 1 now. So I want that to be in here. It's going to be pi plus pi on 3. It'll be pretty good at your fractions to be able to do this. So let's rewrite it. Pi plus pi on 3. In this quadrant, tan is positive. So it's going to be exactly equivalent to tan of pi on 3. Now, some people need to revert to degrees to be able to do exact ratios. I'm one of those. So pi on 3 is 60 degrees. Tan of 60 is root 3. So that's going to be equal to root 3. Now, there's also what we call boundary values, and they're the multiples of 90 degrees. So for sine and cos, these are either going to be 0 or plus or minus 1, and you tend to remember these from the graph. So, for example, sine of 0 is 0, sine of 90 is 1, sine of 180 is 0, sine of 270 is negative 1, and sine of 360 is 0, and similarly for cos. And you also need to know these in radians. Now for tan, they tend to either be equal to 0 or tend towards infinity. Now we can solve trigonometric equations between 0 and 2 pi, and we can get more than one answer. Remember how they are cyclical, these trig graphs? So there's several times where tan theta, for example, is going to be equal to 1. Now we start this by finding the acute angle or the reference angle, and you would have done this like this. So you would have done shift tan of 1, and that gives you 45 degrees, which is pi on 4. Now that gives us the first quadrant angle. There's going to be another one in this range. Now let's draw up our diagram, all stations to central. So we know tan is positive in here. The other place that it's positive is down here, and that's going to be pi plus theta. So we write it out. Tan is also positive in the third quadrant, and so it's going to be equal to pi on 4 and pi plus pi on 4. Again, you've got to work at your fractions. That's going to be 1 plus a quarter. Write it as an improper fraction. It's 5 on 4. So the two answers are pi on 4 or 5 pi on 4. Here's another one. Solve sine theta is equal to negative a half for 0 is less than or equal to theta, less than or equal to 2 pi. Now you can tell from this that we're wanting the answers in radians. If it said 360, then you'd be able to give your answer in degrees. First thing we're going to do is get rid of this negative, because that's going to stop us getting the acute angle. So we ignore the negative and find the reference angle or the first quadrant angle first. And we just do shift sine of a half. That of course is 30 degrees, which is pi on 6. Now let's go to our diagram, all stations to central. We want negative sine. So sine is going to be negative here and here. This is pi plus pi on 6, and this one is 2 pi minus pi on 6. There's the first one. There's the second. Okay, that's going to be 7 pi on 6. This is going to be 12. See where I got the 12 from? 2 times 6. 12 take 1 is 11. 11 pi on 6. So there's our two answers. Okay, one more. Solve cos theta equals 0.2 for negative 180 is less than or equal to theta. It's less than or equal to positive 180. So we've got a little bit of a difference here. We've got degrees, which is nice, but we don't have between 0 and 360. We've got negative 180 to positive 180. That's okay. Still going to do the same thing. Let's find the reference angle. So theta is going to be equal to shift cos or inverse cos of 0.2, which is 78.5 degrees. That's to 3 significant figures. Draw up our all stations to central diagram. Even though this is different, it's still going to be the same quadrants, so we need to find when cos is positive. That's here and here. Now this time, this is going to be 0 plus or theta up to 180, and here's my negative. So this is going to be 0 minus theta. So I'm going to get positive 78.5 and negative 78.5. You can actually check that on your calculator if you want to. Do cos of negative 78.5 and you should get something pretty close to 0.2. The gradient of any straight line is equal to tan theta, where theta is the angle of inclination. And it makes sense because, remember, this is rise over run, and that's also opposite over adjacent. Okay, so tan theta is equal to the gradient. And we can use that to find its equation. So here we've got a line that's inclined at 30 degrees, and its y-intercept is 1. So let's start off by finding the gradient. M is going to equal tan 30, which is 1 on root 3. And we know its y-intercept is 1, so we can just put that straight into the formula y equals mx plus c. And there's our equation of the line, y equals 1 on root 3 x plus 1. So we're going to move on to trig identities from the unit circle, and we met the unit circle in the previous video. And remember, it's just a circle that's centered at 0, 0 and has a radius of 1. And so this distance here is x, this distance is y, and sine theta is equal to y on 1, and cos theta is equal to x on 1. So this any point around here is going to be equal to cos theta sine theta. Here's the first identity. Tan theta is equal to opposite on adjacent, so y on x, sine on cos. So nice little relationship there. And this one's come from Pythagoras' theorem. Y squared plus x squared equals 1. Sine squared plus cos squared equals 1. Both of these are given for you on your formula sheet. So there they are. We could also rearrange them. So that top one there, we could say sine squared theta is equal to 1 minus cos squared theta, just by taking that over there. Or we could say cos squared theta is equal to 1 minus sine squared theta, by taking the sine squared over the other side. Here's a couple of examples. Simplify cos A minus sine A all squared. Now you can split this into two brackets and then do FOIL on it, but by this stage in year 12 you probably should be working a little bit more efficiently. So the shortcut is this one squared minus 2 times this plus this one squared. So writing that out, that's how it looks. Now we can simplify that further. Can you see this cos squared A plus sine squared A thing here? I'm going to just rearrange it so you can see it. That's equal to 1. So 1 minus 2 cos A sine A is the simplest that we can get it at the moment. Something I want to point out just before we move on, and that's this here. So if I do cos A all squared, and a more efficient way of writing that is cos squared A. So those two things are interchangeable. It's not equal to cos A squared. Okay, because in that case only the A is squared. So, but these two are okay. All right, here's the next question. 3 tan x on sine x. Now in this case, it's begging for us to do tan x is equal to sine x on cos x. And rather than do double-decker fractions, I'm going to move this out as a divide by sine, like this. Now let's change that into sine on cos. And now we've got to do division with fractions. Do you remember how to do it? Keep, change, flip. So keep the first one, change the sign, flip the second one. Alright, that's nice and easy. These will cancel out, and I'm going to be left with 3 on cos. We can also factorise trig expressions. This one's the difference of two squares. Can you see that? So I've got a cos x all squared, and 1 squared is 1. So remember, when we're factorising the difference of two squares, I do the square root of both of them, and I'm going to have a positive in the first bracket and a negative in the second bracket. So that's it. Okay, let's just check that out, make sure that makes sense to you. So here I've got cos squared x plus cos x minus cos x, they cancel out, minus 1. Okay, what about this one? I've got a common factor of tan x, so I'm going to take that out. So tan x comes out the front. Tan x times 3 tan x is 3 tan squared x. and then tan x times -1 is negative tan x. This one here, I could make a substitution. I could let m equal sine A and then factorise into the brackets, but this one is a perfect square. It's pretty easy to see. I'm going to have sine A minus 1 all squared. We can use a substitution if required. So suppose we've got factorised 3 cos squared x plus cos x minus 2. I'm going to let m equal cos x. Now let's rewrite that. It's going to be 3m squared plus m minus 2. I want to factorise into the two brackets. You can use the cross method or the Sydney-Hubbard bridge method or the magic method or whatever else that you do. Doesn't matter. I'm just going to factorise it straight into the brackets. Let's just check I'm right. I've got 3m squared. Then I've got plus 3 minus 2m, which is 1m. And then at the end I've got minus 2. Now the last thing I've got to do, and don't forget this part, is substitute back. So it's going to be equal to 3 cos x minus 2 in brackets and then cos x plus 1 in brackets. Another thing that we've got to be able to do is prove that an expression is equal to another expression. So here's an example. Prove that cos x divided by 1 plus sin x plus 1 plus sin x all over cos x is equal to 2 divided by cos x. And what we do here is we start with the left hand side and then work it through until we get the right hand side. So start with this. Okay, what we're going to do here is make a common denominator, and it's going to be 1 plus sin x in brackets multiplied by cos x. Now if we multiply the denominator here by cos x, we've got to do the same to the top. And if we multiply the denominator here by 1 plus sin x, we've got to do the same to the top. So hopefully this makes sense to you. See the common denominator? And I've multiplied the top here by cos x and the top here by 1 plus sin x. Next thing we do is expand this out. So that is 1 squared plus 2 times sin x times 1 plus sin x all squared. Okay, where do we go from here? Sin squared x plus cos squared x is equal to 1. So that 1 there plus this 1 is going to give us 2. So 2 plus 2 sin x, factorise, and this will cancel. And we're going to end up with this. And so it's equal to the right hand side. So once we've worked through from the left hand side and proved that it's equal to the right hand side, we're actually finished. Let's move on to double angle formulas. There are two double angle formulas that we need to know. Sine 2 theta is equal to 2 sine theta cos theta. These are both given for you, by the way, on your formula sheet. And cos 2 theta is equal to cos squared theta minus sine squared theta. I'm not going to go through why they are equal to that. You can look up the proof if you want to. But these are just two identities that you need to know and be able to manipulate. There are a couple of different versions of this one. So we know that sine squared plus cos squared is equal to 1. So we can make substitutions here to get different forms. So here's one of them. So if I make this into 1 minus sine squared, I'm going to get 1 minus 2 sine squared theta. Alternatively, I could make this into 1 minus cos squared, and that will give me this. Okay, so there are a couple of different versions for cos 2 theta, only one version for sine 2 theta. Let's have a look at how we use them. So let's return to this question. We did this earlier in the video. Cos x minus sine x all squared. So we did cos squared x minus 2 times sine x times cos x plus sine squared x. And remember, we found that sine squared x plus cos squared x was equal to 1, and we left this as it was. Now that we know the double angle formulas, we recognise that as sine 2x. And so the full simplification of this question is 1 minus sine 2x. Here's another one, sine 2x divided by 1 plus cos 2x. Now in this case, we're going to make it more complicated in the hopes that things are going to cancel out. So we know sine 2x is 2 sine x cos x. And this one, remember, has got various forms. So cos squared minus sine squared is not going to really help me. What's going to help is this one here, 2 cos squared x minus 1, because then the 1's are going to cancel out like this. So we can cancel those out, and then the 2's are going to cancel, and one of these cos's is going to cancel, which is going to leave us with sin x over cos x, which is tan x. Here's another way they could ask the question. Find the exact value of sin 15 cos 15. Anytime you see a sine next to a cos, you should be thinking about the double angle formula for sine. So sine 2 theta is equal to 2 sine theta cos theta. Suppose then that theta was equal to 15, 2 theta would be 30, and we know the exact values for 30. So let's rewrite it. Sine 15 cos 15 would be a half of sine 30. Let's write that out and make sure you understand. So sine 30 is equal to 2 lots of sine 15 cos 15. So do you see? This part here must be equal to a half, if I take that over the other side, of sine 30. And we know what sine 30 is. It is a half. And so it's going to be equal to a half times a half, which is a quarter. Let's finish off with some trig equations. Recall, when we find the size of an angle, we're solving a trig equation. So we might have a question like this. Solve sine theta is equal to 0.5 for 0 is less than or equal to theta, is less than or equal to 2 pi. We begin by doing shift sine of 0.5 to find the reference angle. And we know that's a half, so it's going to be 30 degrees, but we need it as radians, so that's pi on 6. Then we need to draw up our all stations to central diagram, because there's going to be another angle. Okay, let's see. We want sine being positive, so that's here and here. We've already got the acute angle. This one here is going to be pi take away pi on 6. Just write it as theta. Pi take away pi on 6 is 5 pi on 6. So there's our answer. Now there's another type of question, a trig equation type question, that's going to involve exact values, but they're not the exact values that we know, like 30 degrees, 45 degrees, and 60 degrees. It's a question like this. If sine x is equal to 1/5 and x is acute, find the exact value of tan x. Now, we don't recognise this as one of the exact values. What we do in this case is draw up a right-angled triangle. We put x in here as the angle, and this is 1/5, so that's going to be opposite is 1, hypotenuse is 5. And then we're going to do Pythagoras' theorem on this to get this side here. So it's going to be 25, take 1 is 24, and the square root of 24 is going to be this adjacent side here. Leave it as the square root of 24 because we want exact values, not decimals. Then we want to know what tan x is, so we're just going to do opposite over adjacent, which is 1 on root 24. Now, if it tells me that cos x is going to be less than 0, I'm going to need to adjust my answer a little bit. I'm going to need to go to the all stations to central diagram. So we know that sine is positive. That's either in here or here. And it's telling us that cos is negative, and that's going to be here. So we want to be in this quadrant. We want to find tan x. Tan is going to be negative. It's going to have the same magnitude as the previous answer, but it's just going to be negative. So my answer will be negative 1 on the square root of 24. So we can get harder trig equations like this. Solve tan x and then brackets 2 cos x minus 1 equals 0. For 0 is less than or equal to x is less than or equal to 2 pi. Okay, we're going to use the null factor law here. When we've got a product multiplies to equal 0, either this thing is equal to 0 or this thing is equal to 0. So let's write those out. Tan x equals 0 or 2 cos x minus 1 equals 0. This one here, solving this is going to require some knowledge of the boundary values. So let's draw the graph. When is tan x equal to 0? Here, here, and here. So 0, pi, and 2 pi. Solving this, we'll take the 1 over the other side and then divide by 2. Cos x is equal to a half. Let's do shift cos to begin with to get the acute angle. So that is going to be 60 degrees, which is pi on 3. And then we need to draw up our all stations to central diagram. So we want cos positive. Cos is positive here, which is that one there, and here. And this is 2 pi minus theta, or x actually in this case. So 2 pi minus pi on 3. It's going to be 6 pi minus 1, 5 pi, divided by 3. And so that's our answer. So we're going to give all of these answers. 0, pi, 2 pi, pi on 3, and 5 pi on 3. Here's another one. Solve 2 sine squared x plus sine x minus 1 equals 0 for 0 is less than or equal to x is less than or equal to 2 pi. Now, this is a quadratic, and it needs to either be factorised or we can use the quadratic formula. You might prefer to factorise that. That's okay. I'm going to use the quadratic formula just to show you a different way to do it. So instead of x squared and x here, I'm going to make sine x the thing that I'm finding, if that makes any sense. So I could do a substitution, let m equal sine x, but you actually don't have to. Instead of making m equal this, I'm making sine x equal this. Still going to use the same thing. This is b here, this is a, this is c. So minus b plus or minus the square root of 1 squared minus 4 times 2 times negative 1, all divided by 2 times 2. And tidying that up and working it out, I get a half and negative 1. So I've got two things here that I need to solve. Sine x equals a half and sine x equals negative 1. So let's do sine x equals a half first. We're going to do shift sine of a half. That's one of the exact values, remember. So it's 30 degrees or pi on 6. And we're going to need to do our diagram, all stations to central, to find the other point where, or the other quadrant, where sine is positive. So it's positive here and here. And this is, of course, pi minus pi on 6. Which is going to be 5 pi on 6. And then when we want to do this, this is one of our boundary values. So a quick sketch of the sine curve will help us find that one. And there's only going to be one. It's here. It's 270 degrees, which is 3 pi on 2. And so that's our other one. Last question. Solve sine squared, and then in brackets theta take 60 equals a quarter for 0 is less than or equal to theta, less than or equal to 360. So we're in degrees, not radians. First thing we're going to do is the square root of both sides. And the square root of a quarter is plus or minus a half. The next thing to do is to do shift sine of a half to get our reference angle or our acute angle, and that's 30. Now this time when we draw up our all stations to central diagram, we're going to be in all 4 quadrants. Can you see why? Up here sine is positive, down here sine is negative, and we want both. So we're going to get theta take 60 is equal to 30, 180 minus 30, 180 plus 30, and 360 minus 30. Now add 60 to all of these, gives us 90, 210, 270, 390. Now just before you finish these sorts of questions, that's these ones with a bracket like this, just be very careful, have a look at this here. This 390 is outside of that range, so we're not going to include it. And if that happens, consider that there could be an extra answer here. Alright, so this was the 4th quadrant. So before this quadrant here, this acute quadrant, is minus theta. So an additional possibility here is negative 30. Have a look what happens when we add 60 to that. It jumps into this range. So if you get this happening, consider that there could be an additional one. It might not be in here. It could be 360 plus theta, but either side. So our final answer here is 30, 90, 210 and 270. Let's finish off with a past exam question. This comes from the 2018 paper. It's a paper 1 question, so it's non-calculator. And I'm only going to do parts A and B because C involves calculus. First two terms of an infinite geometric sequence are u1 equals 18 and u2 equals 12 sine squared theta. And theta lies between 0 and 2 pi but doesn't include 0 and 2 pi. And theta is not equal to pi. A, part 1, find an expression for r in terms of theta. So this is a nice easy question. It's a geometric sequence, so r is going to be the second term divided by the first term. And we write it like that, and then simplify by dividing top and bottom by 6 gives us 2 sine squared theta on 3. Part 2, find the possible values of r. So what this is referring to is the fact that it's an infinite geometric sequence, and that means that r has to lie between -1 and 1. So making this substitution, we have this. I would caution you against trying to solve that inequality. It's quite messy and you end up nowhere. We need to instead use some common sense based on sine squared theta. Now, I don't know if you know much about the graph of sine squared theta, but this is a good time to learn it. Sine theta looks like this, and sine squared theta is very similar, except it's never negative. So it sort of comes up like this and bounces up again. And it goes between 0 and 1. So let's look back here at this expression. If this thing here is only ever between 0 and 1, then this whole thing must lie between 0 and 2/3. The maximum it can get is 2/3. And in fact, this is always going to lie between -1 and 1, so it was nothing to do with that. It was to do with the bounds of sine squared theta. So sine squared theta lies between 0 and 1, and so r must lie between 0 and 2/3. One more thing to note. It says up here that theta can't equal 0. So we're not going to put an equal sign here, but there's no problems with theta or sine squared theta equaling 1, so we will have less than or equal to here. Part B, show that the sum of the infinite sequence is 54 divided by 2 plus cos 2 theta. If you couldn't do that previous question, you should be still able to do this one. All we need is this formula. Sum to infinity is u1 divided by 1 minus r. We make the substitution. So there's our 18, and there's our r from before. And first thing we're going to do is tidy this up so I don't have double-decker fractions. So I'm going to make a common denominator here of 3. That'll make that a 3. And I'm going to divide by the reciprocal. So I'm doing quite a bit there. You might need to do an extra step. This 3 has come up the top here. 18 times 3 is 54. We're nearly there. Right, the last thing to do to go from here to here is to look up our double angle formulas. We've got cos 2 theta. We want the sine squared theta version, which is here. So we want 1 minus sine 2 sine squared theta. I'm just going to change that 3 into 2 plus 1. Can you see my 1 minus 2 sine squared theta now? That's cos 2 theta. And so there's our answer.